Okay, couple of procedural announcements here. I know you all are ramping slowly, or maybe not so slowly, into next week's spring break. The plan for Friday is I have your exams graded. I'm going to be handing those back out, spending Friday going over the exams. So there's that info. Grades not too bad. Average was around a 76 with a couple of hundreds thrown in there, so not too bad. Today, right, we're going to be picking back up and talking in greater detail about convection and the equations that make it happen. So, we're going to be focusing on the governing equations for convection. So up to now, right, we have established a few key things. One is that there are such things as velocity and thermal boundary layers, right? The idea that between a fluid flowing past an object and between the properties of the object itself, there has to be a region of transition, and that thin region of transition is called the boundary layer. The velocity boundary layer is where the flow slows down to achieve the zero slip condition at the surface. The thermal boundary layer is where the temperature of the fluid transitions between that at the boundary and that in the fluid. Those two boundary layers are related to one another, but they are not necessarily the same thickness, nor are the distributions of temperature and velocity the same. Okay, so we're going to see that here in just a second. So we should be convinced at this point, right? There should be no doubt remaining that convection is tied closely to the behavior of the flow in that thermal boundary layer. So this leaves a big question, right? We've established that it's tied to the flow. We've established that H, our convection coefficient, is not just a constant number, right? It can change both as a function of the boundary layer's behavior, whether it's laminar or turbulent. It can change along the length within a given boundary layer. And so that one question that remains to be answered is, how do we find H? Okay. Up till now, we've been given H, or we've been given an equation that describes H, but that's not going to be the case in all problems that we encounter in engineering, right? We need the wherewithal to be able to figure out an approximation, if not an exact value of H, when we're given some problem and some information about the flow of a fluid past an object. So the question we're going to be attacking is how to find H. So today we're going to be focusing on a couple of analytical methods. That is, analytical methods, which we could also call exact methods. So this is, how do we approach this using pure theoretical solution? And what we'll find is that, right, we can set up the equations and we can talk about the equations, but except in a few cases we can't solve the equations. So we'll move on next week into correlations, similarity solutions, and ways that we get H and for more complex geometries. But for today we're going to focus on these simpler problems that allow us to actually find H exactly. So where we left off last time, right, was the idea that fluid flow and thermal energy obey three principles. Right. Number one was mass conservation. Number two was momentum conservation, which is more familiar to us as Newton's second law, or F equals MA. And number 3 is energy conservation, which we've discussed as the first law of Thermo, or the out plus the So on the basis of these 3 physical behaviors, right, or physical limitations, we can develop a set of equations that should, in practice or in theory, describe any fluid flow and the way the thermal energy moves around in that fluid, allowing us to do the whole shebang, right? So we're going to list out the governing equations that correspond to each of these. Like I said last time, I'm not going to focus on the derivation. I'm just going to give you the equations. We'll talk a little bit about their interpretation, and then we'll do an example where we solve them exactly. So let's consider a case where we've got some object. We're not going to specify what shape it is, but it could be a flat plate, for example. We've got fluid flowing past it. We don't know what the fluid's doing, but if we have some velocity, we could refer to that velocity as v, which is composed of an x component, which we'll call u, and a y component called v. All right, so 2-dimensional velocity field, u and v. That's all I want to point out here in terms of nomenclature. The assumptions we're going to be using here are 2D flow. It's very easy to extend to 3D from this case, but we'll stick with 2D for now. And incompressible flow. All right. So under these auspices, let's go ahead. 1, conservation of mass takes the following form. This is du dx plus dv dy is equal to 0. Right? You've all seen this before in fluids, where we refer to this as the continuity equation. Okay? And all this is really saying is that the flow that goes into a region of space has to come out of the region of space. All right? There's no accumulation of mass or of volume for incompressible flow. Yeah. Well, I thought I heard a question. Continuity equation. Number 2, Newton's second law goes as follows. Density times du dt. This will be the x component. That is like fx equals m times acceleration in the x direction. Rho du dt plus u du dx plus v du dy negative dp dx plus rho gx plus mu d squared u dx squared plus d squared u dy squared. Okay, and in the y direction, the y component, which would be fy equals may. We have rho, very similar expression, but we just swapped out most of the u's for v's. V, u dv dx plus v dv dy to negative partial p partial y plus rho g y plus mu d squared v dx squared plus d squared v dy squared. So we have our x and y components of momentum conservation, where, right, the idea here is this first term is our local unsteadiness. Right? So we would call this the local or time acceleration. These two terms here would be called the advective acceleration in fluids. Sometimes we also call this the convective acceleration. We'll be a little more rigorous about this here. This here is the pressure gradient. This is the gravitational body force, or the weight of a particle of fluid. And then this is friction, which is also known as momentum diffusion. So the idea here is, right, momentum is mass times velocity, right? Here we've got mass per unit volume, and we've got the rate of change of a bunch of velocities. So we're talking about sort of the acceleration times the mass per unit volume. And so all the terms here on the left-hand side effectively work out to sort of an m times acceleration, right? But per unit volume. So density times acceleration, and all the terms on the right-hand side turn into the sum of the forces in the y direction, also over a per unit volume. So we can see, sort of, if we zoom out, that we're really just talking about that regular F equals ma relationship that we should all be pretty familiar with, just with a lot more terms. Temporal rate of change, the rate of change induced by motion through a spatially changing field, pressure-induced force, weight, and friction. Okay. So taken together, right, when we talk about these in fluids, we knew these sets of equations as the Navier-Stokes equations, right? Navier-Stokes equations. So you have one in the x direction, you have an equation in the y direction, and you have an equation in the z direction if you're talking about a three-dimensional flow. Give you guys a minute to finish writing everything down. And then physical principle number 3, right, was energy conservation. And so this gives rise to what we call the energy equation, which is a restatement of the first law of thermodynamics, and can be written as such: rho c dt plus u dt dx plus v dt dy equal to k squared t dx squared plus d squared t dy squared plus q dot minus mu 2 u dx squared plus 2 dv y squared plus, I gotta zoom out a little bit, du dy plus dv dx squared. All right, so this is the infamous energy equation. And this is one that we did not see in fluids, right? This is a new kid in town. But we should see some parts of this equation that are pretty familiar to us. So we've got our rho c, right, our capacitance, time rate of change. So if we take rho c dt or dt dt, right, this we should recognize from like our unsteady heat equation. Okay, it's just saying the rate of change of thermal energy in per unit volume. Here we've got our convective rates of change, right? If temperature is changing in x or in y, then the rate at which a particle is passing through at those x and y positions will contribute some additional rate of change. So rho c times an effective rate of change. All of this, here on the right-hand side, basically turns into the rate of change of stored thermal plus mechanical, or thermal energy, right? This is all written for thermal energy. Over here, we've got our conductivity and our diffusion. This is another term that should be familiar from our heat equation, right? This is the spreading out of thermal energy. We have our thermal energy generation term here, right? The rate at which stuff that is not thermal becomes thermal. Electrical resistance heating, chemical reactions, nuclear reactions, etc. And then this one is unfamiliar, right? This mu here. Let's finish writing this here. Diffusion, generation, and then this mu. Anyone have any guesses as to what, sort of broadly speaking, right, what this mu term could physically represent? Mu is a symbol used to represent viscosity, right? What happens as a result of viscosity, right? Viscosity and combined with shear stresses creates, or shear flows creates shear stresses, also known as friction. Okay, and friction is really good at generating what? Heat. So this can be thought of as a frictional heating term. In other words, we've got all these shear flows multiplied by friction contributing some amount of thermal energy through viscous dissipation. So we'll go ahead and call this term here viscous dissipation or frictional heating. Okay, so there we have it. We have equations 1, 2, and 3, which taken together, or sets of equations 1, 2, and 3, which taken together, I can't fit them all on the same page, describe conservation of mass, conservation of momentum, and conservation of energy in a flow. All right. So really, physically speaking, these aren't that scary, I hope. Mathematically speaking, these are horrifying, all right? These are what give researchers nightmares because it's a series of coupled, nonlinear, partial differential equations, and there are no solutions to them in general. There are a few special solutions for very simple geometries. We'll do one of those in a minute. But it's important that you kind of get comfortable with what they're saying, because that's going to make life a lot easier. Rate of change of stored energy is equal to diffusion of heat, or thermal energy, plus generation of heat minus dissipation of heat. This should make some sense, right? It's basically saying the same thing that the heat equation is saying, right? Which also makes sense because the heat equation is based on the first law of Thermo, which this is a statement of. So quickly here, I want to, sort of as an aside, to kind of demonstrate some of the physical reasoning behind this. As an aside, what if we were to get rid of temporarily, we were to say, let's forget about this heat generation term and let's get rid of this viscous dissipation term. All right. So hypothetically, if Q dot equals 0 and we're talking about an inviscid fluid. Okay. Approximations to inviscid fluids. Usually air is a pretty well approximated by the inviscid assumption because viscosity of air is very low. Often water can be approximated as an inviscid fluid. Alternatively, we could say, fine, it's a viscous fluid, but if we have no velocity gradients, that is, it's a uniform flow, all right? Or if it's a flow that does not have a net amount of curl in it, okay, then all the DUD, the spatial gradients of velocity will disappear. So anything, either inviscid or shear free flow, something that allows us to get rid of this second term and the energy generation, you can get rid of the Q dot term. What we're left with is known as the advection diffusion equation. Okay, and this is not a different equation. This is just a simpler version of our general energy conservation principle. But this is one that's used a lot in science and engineering. It's just going to say dt. Oh, also, if we divide both sides by this rho c term, right, then we end up with dt plus u dt dx plus v dt dy is equal to k over rho c d squared t dx squared plus d squared t dy squared. So what we've got now, and this k over rho c can also be referred to as gamma, right? Also known as the thermal diffusivity. So this is another term we've seen before. So what we're seeing now is something that should look a lot like our heat equation. Okay, our heat equation, but with the inclusion of now these advection terms. So we're seeing the rate of change of thermal energy at a point plus the rate of change of thermal energy created by advection, that is the sweeping of particles away or into regions where the thermal energy is different, is equal to the diffusion, and this is just Fourier's law. So conductivity plus advection equals time rate of change, or combined with advection gives you the time rate of change. So this is pretty physically easy to understand. So we've got a couple of, if you give me a second here, a couple of videos that I wanted to show you that illustrate what these different phenomena are going to look like. That is not quite the one I wanted. Okay. So, right, if we were to kill off various different terms in this, for example, if we were to first get rid of the advection terms, that is, if we were to say that the u and v are equal to 0, that is, that the flow velocity is equal to 0, then all we have is the unsteady heat equation, right? Agreed? Time rate of change of temperature is equal to this diffusion term. We've already been there, and we've seen it. And what that's going to look like for us is going to be sort of this unsteady spreading out of thermal energy. So if you end up with a hot spot in the middle and you let the time march on, you're going to end up with this slow spreading out of heat. This video doesn't show a very long duration, but right, we've also established that this is difficult to solve exactly. So typically, if you want to evaluate the diffusion equation, you're going to do it using a numerical method like the two-dimensional heat equation, finite differencing, that you coded up for homework 4, combined with something that captures another finite difference that captures the rate of change of time. And if you were to do that, you'd end up with an animation that looks like the one on the right. So diffusion is equivalent to spreading out. If we were to get rid of the diffusion term, all right, if we were to say the diffusivity is equal to 0, in other words, this would be the same as saying the conductivity is equal to 0. Okay, this would be a perfect insulating material, something that doesn't transfer heat to between adjacent molecules. Right? In that case, we'd end up with what's known as the pure advection equation, which says that a region, all right, a blob of hot temperatures placed into a current or into a flow is simply going to move with the flow. If we leave both of those equations in place, or both those terms in place, we say, fine, temperature is allowed to diffuse and it's allowed to advect, then the general advection diffusion, which is also known as the convection problem, right? Combination of conduction and advection is going to look like a combination of the two behaviors. The temperatures are going to be advected as well as spreading out. Okay, and then sort of as a, we'll call this, so that's a special version of the energy equation, right? The advection diffusion equation. There's also an analog here that we should mention for our conservation of mass. There's a special term here known as the species equation. So this has to do with this conservation of mass when when two fluids or two concentrations are present. For example, if you were to mix, dump a bunch of salt into water, right? You're going to end up with some concentration of that salt. You would call that salt a species, which is being dissolved into another species, that being the H2O molecules. So if you were to apply conservation of mass there, clearly you have to account for the fact that there's only so much salt and there's only so much water. So you have to do the bookkeeping for those separately. And so the species equation can be written this way. And we're not going to do a whole lot with the species equation, but it's good that you have this written down, because this is a classic and fundamental component of heat and mass transfer. V dCA dy equal to dy squared plus n dot. All right. So in this equation, Ca is a concentration of species A, which is generally given in kilomole per meter cubed. Okay, so it's an amount of matter per unit volume. dA, right? Let's look at an analog to our heat equation. Generally, we've got over here our second derivatives. What was this term in our heat equation? Okay. This was when you had the second derivatives multiplied by something. This was our diffusion, right? The spreading out. So just like the heat equation and our species equation, this is our diffusion. That's the spreading out of your concentration in a fluid. And so that D sub A term we refer to as the species diffusivity. Okay, so again, if you were to dump a bunch of salt into a bucket of water, that D sub A is going to give you some information about how quickly it spreads out or diffuses through that body of fluid. And N, right, is the species generation rate, generally due to a chemical reaction. So what happens when you mix an acid and a base, right? The two are going to neutralize and create, as a byproduct, some sort of salt. So let's say we've got a flow of an acid and a base mixed together. Where the two interact, you're going to end up with some volumetric generation of a type of salt. That salt is going to be diffusing, advecting with the flow, and it's going to be continually being created by the ongoing neutralization of the acid and the base. Okay, so this is generally tied to the chemistry of the flow. So very important. All the math here, right, is identical to what we're talking about for thermal energy. So that's why I want to write this down, is we can see that the way that mass advects, diffuses, and gets generated is identical in terms of its governing equations to the way that thermal energy advects, diffuses, or conducts, and is generated. So with the tools that we're going to use to solve the thermal energy governing equations, or the energy equation, you can apply the same stuff to the species equation. That's all we're going to say about species conservation for now. But make sure you have that kind of in the back of your head. So, on to the question of the day, right? So we've established the governing equations, but I want to return to what we're really looking for is right, how to find, H. Right, how do we boil down these nasty, unsolvable nightmare equations to a convection coefficient? So, a couple of solutions, right? We might say we've got the governing equations, right? Plus we've got this expression we derived earlier that says H is equal to negative K sub F times dt dy, y equals 0, all over Ts minus T infinity. So our first inclination, sort of a naive approach, might be would be, okay, let's take the governing equations we've got up top, solve our continuity plus momentum equations, and we get out U and V, right, in a perfect world. If we can solve those, we'll get out of a velocity distribution. Take those U and V, right, and plug into the energy equation, right, and solve for the temperature. Okay, take that temperature, plug into, if we call this guy here, we'll call this star, into star, and find H. Okay, so here's the logical progression that we would want to follow. Figure out what the flow looks like. Use that flow character to figure out what the thermal energy is doing in that flow, and then use the distribution of thermal energy and the temperature distribution to find our convective heat transfer coefficient. This is a long and laborious set of steps, and generally speaking, it's not possible. Right? We just said that most of the time these equations are unsolvable. Ultimately, where we're going, like I said, is going to be figuring out how to shortcut around these actual solutions, because we can't achieve those. But, as I said, there are a few special cases where we can solve this. So let's see what this process looks like with a problem where we can actually go through all these steps, and then we'll talk about what we do when we can't go through all of those steps. So, example, this is another thing that you've seen in fluids, but we're going to add thermal energy into it. This is an example of what we call Couette flow. So in Couette flow, we're going to assume, come on, there we go, that we have two parallel walls. Okay, these walls are going to be assumed to be infinitely long. Infinitely long wall. So this bottom wall here, we're going to say is fixed. That is, it has a velocity of 0. This upper wall, we're going to assume is moving with u equals u sub t. Okay. So this could be considered similar to the way like a linear bearing works, where we have a fixed surface and another surface sliding past it. And between these two walls, we've got some fluid, which we'll assume to be a Newtonian fluid, such as water, air, oil, what have you. We'll say that these two surfaces are located a distance big H apart from one another. And that they both have different temperatures. So the top here we'll say has a temperature T sub T, and the bottom temperature T sub B. Okay. So our assumptions for this problem, right? The things that are unsaid that are going to make this easier to solve. Assumptions are as follows: that v equals 0. That is, let's set up our coordinate system. We'd say x and y, okay, and z is going to go infinitely into the page. So we're going to say v is equal to is equal to w is equal to 0. In other words, the flow is in the x direction only. We're also going to assume that there's no gravity. It wouldn't make much of a difference if we included gravity, but we'll leave it out for now. We're going to assume that we're at steady state, that the temperature is a function of y only, that is, that the temperature does not vary in the x direction. And we're going to assume that, let's say we have a a pressure over here, we'll say P1. Over here we have a pressure, P2. We'd assume that P1 is equal to P2, or in other words, that this is not a pressure-driven flow. Okay, under these assumptions, which are pretty restrictive assumptions, okay, this is a pretty serious set of assumptions to apply to a problem. That's the only reason that we're going to be able to solve it. Okay. But under these assumptions, we can start to write out our governing equations. Let's start out with the easiest one, which is continuity. Okay, that's only got a few terms involved. So continuity equation du dx plus dv dy is equal to 0. The idea is, right, if v is equal to 0, then any gradient of v is also going to be equal to 0. So we get to kill this term off. What we're left with is then that du dx is equal to 0, which tells us that the flow is, anyone remember this from fluids, what we call it when it's not changing in the direction of flow anymore? It's called fully developed, right? Means the flow over here is the same as the flow right here, is the same as the flow right here, is the same as the flow 100 miles down that way. Okay. Momentum equation. Since we said that, right, u is the only velocity component that is appreciable, we said that v is equal to 0, w is equal to 0, then the only momentum that we need to worry about is the x direction, right? Does this make sense? Yes. So the x component of the momentum direction, or momentum equation, is going to look like rho du dt plus u du dx plus v du dy equal to negative dp dx plus rho gx plus mu du squared u dx squared plus d squared u dy squared. All right, it's going to be a matter of hunting down terms that we get to cancel out. So, assumptions. V is equal to, w is equal to 0. Anything that involves a v, let's get rid of it. So, this term here, gone. V is equal to 0, or rather, I should probably cancel that term. Right? V is equal to 0. No gravity. Let's get rid of our g sub x term. Steady state means any temporal terms go to 0. Temperature as a function of f, is a function of y. We're not quite there yet. We're not talking temperature. P1 equals P2. That means there's no pressure gradient. P dx goes to 0. And then if we look at our solution from the continuity equation, right, that du dx is equal to 0, that's fully developed. That also means, so that means that du dx here goes to 0, and the second derivative of u with respect to x is also going to be 0, because it's another derivative of a constant. So what we're left with is going to be e squared u, ui squared, right, mu, equal to 0. Right? We can divide through by mu and just end up with d squared u dy squared equal to 0. So u is going to have a general solution that looks like C1y plus C2. Okay. We might have to finish up the energy equation solution part of this on Friday, but we'll get through the velocity today at least. So at this point, we've got our general solution, just like with heat equation. Once we have the general solution, we have to do what? Apply boundary conditions, right? Apply boundary conditions. So the first boundary condition is going to be, well, we've got two of them to work with, right? These ones are pretty simple. At the bottom, we've got that u is equal to 0, and at the top, we've got that u is equal to something u sub t, right, which is non-zero. So number one, let's say u equals 0 at y equals 0. What this is going to turn into then is if we plug in a 0 for y, this just turns into C2 is equal to 0. Boundary condition number 2, we have that u is equal to ut at y equals big H. That is, once we're at the top plate. So we have that ut is equal to C1 times H. So C1 would be equal to ut over H. Plugging in these values of C1 and C2, we get that u is equal to ut y over H, which just tells us that u y, this tells us that the velocity goes from 0 at the bottom plate linearly up to the velocity of the top plate. So it satisfies the non-slip condition down here, satisfies the non-slip condition up here, and goes linearly across that. So velocity distribution, linear. Okay, we've solved the Navier-Stokes equation for Couette flow. This is, as I said, a classic solution. Yeah, we've got enough time to quickly do the energy equation as well. So from the energy equation, we've got rho c, okay, partial t plus u dt dx plus v dt dy equal to k d squared u dx squared plus t squared. Sorry, that should be t squared dy squared plus q dot minus mu 2 du dx squared plus 2 dv dy squared plus du dy plus dv dx squared. All right, well, at least we'll get through the cancellation process here. So once again, steady flow, we can cancel that out. We've said that only u velocities are appreciable, so anything with a v goes away. That goes away. That goes away. That goes away. Those all involve v's. We've said that du dx is equal to 0, so that there goes away. We've said that the temperature is a function only of x. So any variation of temperature with y goes to 0. Oh, sorry. No, sorry. We said temperature is only a function of y. So any variation of temperature with x goes to 0. That was my mistake. Let me erase. There we go. So here, because t is equal to f of y only, and we didn't actually say it, but we'll go ahead and add this assumption in now that we're not talking about any heat generation. Right? There's no thermonuclear reaction going on in this Couette flow. So our solution at the end of the day here works out to the following: d squared t dy squared minus mu du dy squared is equal to 0. This should be k. Or d squared t over dy squared equal to mu over k du dy squared. Du dy. We know this, right? We know this from the previous solution, the one for the velocity. If u is equal to ut over h times y, then du dy is just equal to ut over h. So if we plug that in, we end up with d squared t dy squared is equal to mu over k ut squared over h squared. And now we've got a constant over on this side and a second derivative on this side. So we can just integrate twice to find the general solution, and we'll leave off with the general solution, which is t equal to negative mu over 2k ut squared over h squared y squared plus c1 y plus c2. So it's going to come down to using the boundary conditions to find C1 and C2, and we'll pick that back up on Friday. There's only a few more steps left to finally get the solution here.